Instruments in Chromaphone 3 are created by forming pairs of acoustic resonators that are excited by either a mallet or noise source or a combination of the two. Here, we're working with only one pair of resonators in layer A, and I have the second one turned off with the balance slider all the way to the first one so that we can focus on the properties. Now, to choose between the different resonators available, we can either use this drop-down menu or simply click on the icon. The string represents a perfectly elastic string. We use this menu to determine the mode density, in other words, the number of partials that are generated. So there are different harmonics. Next, we have a beam, which is a rectangular beam. It has a constant cross-section, and again, a choice of the partials and harmonics. We have a marimba beam with a variable section. Next is a drumhead. It's a circular membrane. And then we have a rectangular membrane, again with different options. Next we have a plate, a rectangular plate. A closed tube is a cylindrical tube with one end closed, and it allows us to get only odd harmonics. The open tube is a cylindrical tube with both ends open, where we can get the complete harmonic series, even and odd. And in the manual mode, we create our own custom resonator by selecting up to 4 partials and dialing them in. Let's go back to string and explore the parameters. The pitch parameter adjusts the frequency of the first partial in semitones and cents. So you can get tuning between semitones. I'm going to double click and it'll return it to its default. But I'm going to leave it transposed up an octave, or 12 semitones. The key control determines how the pitch is tracked across the keyboard. When it's a value of 1, as it is now, that means we get an equal semitone for each semitone on the keyboard. But we can change the tuning and temperament between the semitones on the keyboard. We get some nice enharmonic effects and tonalities. I'm going to double click, and that'll return it to its default mapping of semitone for each semitone on the keyboard. We use the LFO slider to dial in the amount of LFO we want applied to the pitch, and we set the LFO parameters in this module. So it's modulating the pitch, in this case based on a sine wave or a different shape at this rate. And we can sync it to tempo, delay the onset, offset the phase, and create a wider oscillation or narrower. Let's switch to a marimba bar, and here we can defy the laws of physics by applying a pitch envelope to a marimba, which isn't possible in the physical world. We can apply a positive or negative amount. I'll dial down for a negative amount, and this determines the speed of the pitch drop. It's a much longer one versus a quicker one. Or we can go in positive territory, where the envelope starts above the triggered pitch and then scoops down to it based on the speed set by the rate slider. And the velocity slider is used for velocity to affect the pitch envelope based on how hard the notes are struck or triggered. The decay knob determines the overall decay of the object for more staccato sound versus more legato. And the release knob acts as a kind of damper, and it works in relation to the decay value. So it's dampening the partials, or leaving them ring wide open, again, based on the value here. And what's really interesting is that the decay time can be modulated by key tracking or velocity. So by clicking and dialing this up, we can get different decay times over different ranges in the keyboard. So the top notes are very muted, where the bottom ones are ringing out, versus the opposite. I can double click to reset it. Same with velocity. With the velocity, the note affects the damping and decaying. When we dial the material knob down, it causes the higher partials to decay quicker than the lower ones. So we have more low frequency content. In positive territory, the lower partials decay first. So this is relating to the timbre, not the range. Where material influences the decay of the partials, the tone control influences the amplitude. So when we dial it down in negative values, the higher partials have less amplitude, so we hear a thicker, richer low end. And in positive territory, the lower partials have less amplitude, and we hear more of the higher ones. And the low cut acts as a traditional kind of filter, where it just filters out low end. Let's switch to a tube. Here the material is replaced by the radius, which roughly acts as a resonant high-pass filter. Turning the radius clockwise increases both the cutoff frequency of the filter and the decay time of the partials. And the same thing works with the open tube. Let's go back to a beam. And we have a hit position knob, which influences where the mallet or the noise source is striking the object. This is an important parameter related to performance. Just like on a real instrument, it affects the relative amplitude of the different partials of the resonator, and therefore the spectrum or color of the sound radiated by the object. This position is indicated as a percentage of the total size of the object. The minimum value of the control corresponds to an excitation applied on the border of the object, while the maximum value corresponds to an excitation applied in its center position. And we can also modulate these with key tracking. So the range is influencing the hit position. And we can reverse the direction by dialing counterclockwise. Double click will reset it, and similarly with velocity. And we can have random modulation. I'll double click that to reset it, and dial up random hit position. So there we get some nice variety. Let's turn on Resonator B. With coupling mode enabled, Resonator A receives the excitation signal and energy is exchanged between the two resonators through the coupling, creating a new virtual object, dependent on the parameters set for each. The balance slider is used to adjust the impedance ratio, how easy it is to set one object into motion compared to the other. When coupling is disabled, the resonators are not coupled and excited simultaneously. They're in a parallel configuration where the output is a mix of the signals from the two resonators determined by the balance slider.